Soft matter is a branch of science people encounter multiple times a day, often without realising, like brushing your teeth with toothpaste, eating ice cream or pasta, or washing your hair with shampoo. As the name and the example suggest, soft matter is a class of materials which are strongly susceptible to changes in their physical environment and alter or deform their structure as a result of these changes. We want to find out the relationship between the shape and the type of soft matter building block and the resulting material properties. The way these materials behave is determined by their design on an extremely small scale. Let's take a closer look at these materials and travel inside them to the scale of their micro and nanoscopic structure. We live in a world where we measure things on the order of several meters, in contrast to insects who inhabit a scale on the order of millimeters. By using a microscope, we can see what occupies a scale 1,000 times smaller, where distances are measured in terms of microns. At around 2 to 5 microns, we encounter biologically sized systems like blood cells. We can even go 1,000 times smaller if we use a more powerful microscope and reach the nanoscopic scale where individual large molecules are found, like DNA. The array of building blocks in soft matter is very diverse. Examples include colloids, polymers, glasses, gels, membranes, and surfactants. The micro and nanoscale is where the texture, taste, colour, elasticity, and other properties of soft matter are determined. In our group, we design soft matter materials at a supramolecular level to make them behave as we need. But hold on a minute, let's forget about toothpaste for now. There is another common phenomenon that we can make use of. It's what makes your holiday souvenirs stick to your fridge and a compass able to tell you which way you are going. It is, of course, magnetism. There is a special kind of soft matter whose mini building blocks are magnetic. Unsurprisingly, it is called magnetic soft matter, and it is the main subject of our research. Mini magnets can be moved by an external magnetic field. This has potential applications in targeted drug treatments. The idea is to inject a solution containing many tiny magnets covered with the active drug into the patient's bloodstream. The particles can then be delivered to the target region in the body, such as a tumour or a damaged organ, with the help of an external magnetic field. Another very different usage involves the assembly of these mini magnets into various structures, like chains. To illustrate the usefulness of this effect, let's pour a suspension of mini magnets into a jar. In the absence of an external magnetic field, we can easily stir the suspension with a spoon, as the liquid remains watery. Let's now apply a horizontal magnetic field. The mini magnets will now form chains in the direction of the field, which can even grow from one side to the other. Now, if we try to stir the suspension once again, we find that it has become more difficult. It is like stirring black honey. The formation of chains has increased the suspension's viscosity. This phenomenon is called the magneto-viscous effect and is used in high-tech applications, for example, dampers, loudspeakers, and magnetic seals. What makes the applications we just discussed possible? How does it work?